Welcome to the last part of the problem-solving session for Chapter 12. We begin where we left off, question 5. A uniform horizontal beam. Okay, that means that the mass is uniformly distributed. Has a length of 8 meters and a weight of 200 newtons. It is attached to a wall by a pin connection. Here it is. If you can, where's my pencil? There we go. There's the pin connection. So that's where the attachment occurs. The wall exerts a force R on the beam at the pivot point, which, as you can see here, is at some angle to the horizontal, yet to be determined. The far end of the beam is supported by a cable that exerts a tension at an angle of 53 degrees. See, this is the tension here. So we've got R over here. We've got T over here. And we know the angle that T makes with the horizontal, but we don't know the angle that R makes with the horizontal. A person who weighs 600 newtons stands at a distance of 2 meters from the wall. Okay, so here's the person. This distance is 2 meters from the wall, and the person has a weight of 600 newtons. The question is, although not stated here, the question is find the following. Find the force R that the wall exerts, find the force T of tension, and find the angle theta that R makes with the horizontal. How many unknowns is that? 3 unknowns, which means we need 3 equations to solve for these unknowns. Without the 3 equations, we are unable to solve for the unknowns. Okay, so what are we going to do to get 3 equations? Well, how about this? Let one equation be the net force in the y direction, and here we're working in equilibrium, so we set that equal to 0. Let another equation possibly come from setting all the x components equal to 0. See what comes out of that. And let the third equation be the expression that relates all the torques that would produce a clockwise rotation and sets them equal to all the torques that would produce a counterclockwise rotation. These 3 equations will allow us to solve for the 3 unknowns. So let's begin systematically and look at all the forces that act along the y direction. Well, let's see. We've got an Ry. We've got a T sine of 53 degrees, which is positive. Let's see if we can just draw this out here. Here is Tx, which points in the negative x direction. If this is an xy coordinate system, Ty is positive. There's Ty. Here's our x that points along the positive x direction. Here's our y. And we already have the weight of the board, 200 newtons, the weight of the man, 600 newtons. So we're set to go. All right, Ry positive, Ty positive, and I'm going to just write in terms to Ty in terms of T times the sine of 53 so that I don't have to go back later on and insert that angle of 53 degrees. And by the way, we can't assume that theta, the angle that R makes, is 53 degrees. In fact, we'll find that it is not that value. Okay, so we have minus 600 newtons, minus 200 newtons, and the whole thing equals 0. So this equation yields Ry plus t sine of 53, for some reason I'm having a little bit of trouble writing, is equal to 800 newtons. In fact, I think I'm going to have to, sorry if this is going to hurt your ears, but I have to get the pencil here because that seems to be a little bit smoother to write with this. I don't know why, but it is. Okay, so there's our first equation. And this equation contains two unknowns. T, or actually contains all three. T, R, and the sine of theta, in other words, theta. All right, let's go to our second equation. Here, we've got our x along the positive direction minus t cosine of 53 degrees equaling 0. And that gives us the equation that relates Rx equals t times the cosine of 53 degrees. And again, we've got three unknowns here, t, r, and theta, since Rx is there, which means it's r cosine theta. All right, last. Now, here is where we have to decide about which point we would want the axis of rotation. Remember that no rotation occurs. This is an equilibrium problem, but we must choose a location to take the torques so that if the rotation was occurring about that point, we could define the torques. And I choose that point to be right here at the left end. The reason being that I can eliminate one of the, in fact, two of the unknowns. We can eliminate not only r, but the angle theta. We know that this moment arm has been given to us as 2 meters. That's the distance from the man. So d of the weight of the man, d sub m, for example, is 2 meters. We know d to the weight of the board, dB, is 4 meters, they tell us. And we know t, okay, t, and here you can see that ty component is the component that is perpendicular to the length of the board. So d of t is equal to 8 meters. Okay, and something else to notice here, but we're going to use ty when we torque. If we didn't want to use ty and we extend the line of force along the direction that t acts, okay, a direction perpendicular to that, for example, would be this, so that this moment arm would be equal to, this is the right angle of the triangle, this is the hypotenuse, which is 8 meters, so this distance here, dt, would be equal to 8 meters times the sine of 53 degrees, okay? And if you notice here, ty is equal to t times the sine of 53 degrees. So whether we choose to take this as the torque, t times t sine of 53 times d, okay, which is 8 meters, or we take we take the full of t times sine of 53 degrees times 8 meters, notice that we get the same expression for torque. So it really doesn't matter what we choose to do here. It's just a different way to express the very same thing. Anyhow, let's look at the directions of the torques that the torques will produce. The weight of the man produces a clockwise torque. The weight of the board produces a clockwise torque. So we've got two clockwise torques. We've got tension producing a counterclockwise torque. So two clockwise torques, one counterclockwise torque. So let's see. Clockwise torque 600 newtons, the weight of the man, times his location from the axis of rotation, 2 meters, plus 200 newtons, the weight of the board, times its location to the axis of rotation, equals T sine of 53 times 8 meters, or T times 8 meters sine of 53, same thing. So what do we get here? We get 1200 plus 800 gives us 2000 newtons meter, divided by 8 meters times the sine of 53. That immediately gives us a solution for T, which is 313 newtons. Okay, so now we have T. Okay, well, can we get R sub x? Sure we can. R sub x, or in other words, R times the cosine of theta, the unknown theta, is equal to 313 newtons times cosine of 53. And we get then, if we go back up, we get R equal to 188.4 newtons, and we're going to divide that by the cosine theta. The reason we're going to do that is because once we've got R, we can now come up to the expression for Ry, where we determined that Ry is equal to 800 minus T, 313 newtons, times the sine of 53. That gives us 550 newtons, which is equal to R times the sine of theta. Okay, now what we're going to do is we're going to substitute 188.4 divided by cosine theta into this term here, 188.4 divided by cosine theta multiplied by the sine of theta, effectively giving us the tangent of theta, setting that equal to 550 newtons, gives us inverse tangent, and therefore a way to determine the angle. The inverse tangent of 2.92, telling us that the angle is 71.1 degrees. So to get R, so we now have theta, we have T. To get R, just plug in that angle. R equals 550 newtons divided by sine of 71.1, and therefore R is 581.4 newtons. So notice what we did here. We set up the three equations that contain the three unknowns, and we systematically solved for each of the quantities and use substitution to get the remaining unknown quantities. Okay, the last problem here is, oh, actually, it's not the last problem, it's next to the last problem. Question 6 is a ladder of length L which rests against a smooth vertical wall. The mass of the ladder is M, and it's because it's a uniform ladder, the mass is located at its center of gravity or center of mass. The coefficient of static friction between the ladder and the ground is 0.4. Mu s is 0.4. And we're asked to determine the angle theta at which the ladder will not undergo any motion. In other words, we want the largest angle of theta for which the ladder is not going to experience kinetic friction, in other words, movement. Okay, so the unknowns here is the angle theta. Okay, what are the forces that are acting on our ladder? Well, we've got the weight of the ladder at its center of gravity, mg. We've got the wall exerting a horizontal force, which our book labels as P, we could call F, whichever, doesn't matter, because of the contact that is made. In a sense, it's like a normal force, isn't it? Because it's the force that the wall exerts on the ladder. But we also have a normal force here, different from P, which is at the bottom of the ladder, and that's the normal force that the ground exerts on the ladder. And since we are trying to prevent motion, F sub s points to the left. In other words, to keep this ladder from sliding, therefore movement to the right. So we're asked to determine this angle theta, but notice that we do not know n, and therefore we don't know F sub s, only that it's mu s times n, and we don't know P. So how can we go about getting these? Well, as soon as we know n, we'll know F sub s. So that will be cleared up. We're going to use, so we got theta, n, and P. We're going to use the same three equations used previously, but you'll find that the problem is much easier. Let's start with Newton's second law along the y direction. We've got positive n minus mg equals 0. That immediately tells us that n equals mg. Guess what? We've eliminated one of the unknowns. Also, then, Fs equals mu s times mg. Okay, the other related quantity. As soon as we know n, we know F sub s. And remember that this was 0.4. This was given to us as 0.4. All right, what about Newton's second law in the x direction, setting that equal to 0? Well, here we've got minus p, which is entirely horizontal, plus F sub s, which is mu s times mg, equaling 0. Well, this then tells us that P is equal to mu s mg. So another unknown. Lastly, to get the angle theta, which is what they really wanted us to solve for, we're going to look at the torques about some axis of rotation so that equilibrium is maintained. And I suggest that the axis of rotation that we choose be right here to eliminate these two forces from producing torques. And our task now is to find moment arms. Well, let's see. The line of force that extends along P then has a moment arm d sub p, which is equal to the length of the ladder. See, here's our hypotenuse, which is L. So d sub p then is equal to, this is the, if this is theta here, then this is the angle theta. So d sub p equals L times the sine of theta. Okay, that gives us this, the length of this side right here. And mg also has a moment arm. That moment arm is right here. See, that makes a right angle. Here mg is at, this hypotenuse is L over 2. And the side that we want is adjacent to the angle, so d sub mg, in other words, the d associated with the weight of the board, is equal to L over 2 times the cosine of theta. And we can see that mg produces a clockwise torque, P produces a counterclockwise torque, and N and F sub s will not produce any torque since the moment arm is 0. They are at the point of interest. So torque clockwise equals torque counterclockwise. That gives us, let's see, mg L over 2 cosine theta equals P times L sine theta, but P is mu S mg times L sine of theta. Let's see, we can cancel mgl, mgl, and we're left with, if we divide both sides by cosine theta, we have mu s times the tangent of theta equals a half. Now we take tangent of theta equals 1 over 0.4, which is mu s, times 2. So theta is the inverse tangent of this quantity, which gives us a theta of 51.3 degrees. So in other words, that is the largest value of theta for which this ladder experiences no motion. Okay, last problem here. We are told that the arrangement shown below is used to determine the center of mass of an object. It's a light plank. In other words, we're to assume that it has no weight whatsoever, which is not right, but this is what we're told to do. And this light plank is resting on two scales. The reading on these scales is 380 newtons for the left-hand side or at the head, and 320 newtons on the right-hand side or at the feet. We are told that the separation between the scales, which by the way appears to be the height of this lady, and by the way that would make her quite tall, over 6'6" tall. Anyhow, we are trying to locate her center of mass, okay, or her center of gravity, whichever way we want to say it. And let's just hypothetically say that it occurs, let's say, at this location. We don't know, but we're going to assume that it's at this location here. Now, the thing is this. If this is that location and we label that to be x, then this distance here would be labeled as 2 minus x, okay? So we're trying to determine what the value of x is. Now, here's the thing. We also have to consider her weight, okay, which is downward, and, oops, sorry, let's just say that it's right there. This would be incorrect because we want her weight to be at the center of gravity. Her weight, mg. And now we can take Newton's second law in the y direction, set that equal to 0, and we see that we've got three forces. Now, each of the scales supports her. So, in fact, the reading is the normal force on the scale. So we've got upward 380 newtons plus upward 320 newtons minus her weight downward. So we can easily see that her weight is equal to 700 newtons, 380 plus 320. This is her weight. We weren't asked to determine it, but in the process, we've managed to solve for it. Okay, now to solve for what we were really asked for, and that is to determine x. Well, what we're going to do is to take the torques about, let's say, her center of gravity, so that we have this force exerts a torque which would produce a rotation which is clockwise, and it's at a distance x from the axis of rotation. This torque produces a counterclockwise torque at a distance 2 minus x from the axis of rotation. So torque clockwise equals torque counterclockwise. So we've got 380 newtons times x equals 320 newtons times 2 minus x, and of course mg exerts no torque since it is at the axis of rotation. There's no moment arm. So let's just get rid of the unit Newton for the time being. We've got 380x equals 640 minus 320x. We put all the x's together. 380 plus 320 is 700x equals 640x, then equals 0.914 meters. And what that means then is that that is the location of her center of gravity from her head. So in other words, if her height is 2 meters, less than 1 meter is her center of gravity. So her center of gravity would be just above her midsection, or midpoint, I should say. Okay, so this concludes the last part of the problem solving session for chapter 12. Until next time.